This diagram depicts the architecture of a radio frequency adversarial learning, RFAL, generative adversarial network, GAN. Let's break down the components and flow of the architecture step by step. Detailed explanation. Random signal generation. A random signal is generated, which forms the basis for the adversarial input. This signal is modulated using quadrature phase shift keying, QPSK, modulation. QPSK modulation. This modulation scheme is applied to the random signal, preparing it for transmission. Transmission, TX, via USRP 9210 Pluto. The modulated signal is transmitted using hardware like the USRP 9210 or Pluto software-defined radios, SDRs. Reception and training data collection. A trusted receiver collects the IQ data from an RTL SDR, a type of SDR, for training purposes. This data consists of complex samples that represent the transmitted signals in the IQ plane. This received training data is used to train the discriminator, D, and the generator, G, within the GAN. Latent space. Adversarial components. Modulation scheme, M, T, represents the type of modulation used. Signal amplitude, A, T, represents the amplitude of the signal. Signal phase, represents the phase of the signal. These components form the latent space, which feeds into the adversarial process. Noise vector, G, T, and generator, G. A noise vector, N, T, is added to the latent space components to generate adversarial signals. The generator, G, creates counterfeit samples, S, T, from this noisy latent space. Feature extraction. Features are extracted from both the trusted training IQ data and the generated counterfeit samples. These features are used to train the discriminator. Discriminator, D. The discriminator, D, is pre-trained using the trusted IQ data. It then evaluates the generated counterfeit samples to determine if they are real, trusted, or fake, counterfeit. The discriminator is fine-tuned during the adversarial training process. Training objective. The GAN is trained using a minimax objective function, where the generator tries to minimize the discriminator's ability to distinguish between real and fake samples. Minute. Max. Sigma. Equals. 1. Log. Plus. Log. 1. Theta. G. Minute. Theta. D. Max. I equals 1. Sigma. M. Log D. X. I. Plus log 1d, g, z, I. Here, theta, g, and theta, d, are the parameters of the generator and discriminator, respectively. X, I, are real samples, and g, z, I, are generated samples from noise. Z. Prediction and verification. The discriminator outputs predicted labels for the generated data. The predicted labels are used to verify if the discriminator's judgment is correct. This output helps determine if the data is trusted or counterfeit. Script explanation. Python. Copy code. Def explain _RFAL _GAN architecture. This function provides a detailed explanation of the RFAL GAN architecture based on the given diagram. Step 1. Random signal generation. Print. Step 1. A random signal is generated and modulated using QPSK modulation. Step 2. Transmission, TX, via USRP 9210 Pluto. Print. Step 2. The modulated signal is transmitted using hardware like the USRP 9210 or Pluto SDRs. Step 3. Reception and training data collection. Print. Step 3. A trusted receiver collects IQ data from an RTL SDR for training purposes. Print. This data consists of complex samples representing the transmitted signals in the IQ plane. Step 4. Latent space and adversarial components. Print. Step 4. The latent space consists of the modulation scheme, signal amplitude, and signal phase. Print. These components feed into the adversarial process. Step 5. Noise vector and generator, G. Print. Step 5. A noise vector is added to the latent space components to generate adversarial signals. Print. The generator creates counterfeit samples from this noisy latent space. Step 6. Feature extraction. Print. Step 6. Features are extracted from both the trusted training IQ data and the generated counterfeit samples. Print. These features are used to train the discriminator. Step 7. Discriminator, D. Print. Step 7. The discriminator is pre-trained using the trusted IQ data and evaluates the generated counterfeit samples. Print. It determines if the samples are real, trusted, or fake, counterfeit. Print. The discriminator is fine-tuned during the adversarial training process. Step 8. Training objective. Print. Step 8. The GAN is trained using a minimax objective function. Print. Min_G max_D, log D, x, plus log, 1 D, G, Z. Print. Where G and D are the generator and discriminator, respectively. Step 9. Prediction and verification. Print. Step 9. The discriminator outputs predicted labels for the generated data. Print. The predicted labels help verify if the data is trusted or counterfeit. Run the explanation function. Explain _RFAL _GAN architecture. This script provides a step-by-step explanation of the RFAL GAN architecture, aligning with the diagram provided. Each print statement corresponds to a specific part of the architecture, ensuring a comprehensive understanding.